Okay. So today I want actually to finalize discussing about mathematical logic by giving you the final actually point here. So I don't know, Lima is absent.
Yeah.
You know that he's not coming?
Wasn't here during history lesson. Maybe he's coming via Zoom.
I'm not on Zoom, unfortunately. I'm always on YouTube now. So hopefully he knows about that. Okay.
Should I inform her?
Yeah, we can. It's public. It doesn't need any link. So I see one person is here, but I don't know who it is.
It's probably Lou.
It's public actually. So let us talk about this last part, introductory predicate logic. So let me just start with the definition of a predicate. Yes. So definition. So a declarative sentence is said to be, is called a predicate or an open statement if there are three conditions. If it contains some variables two, it is not a statement. Three, let me write here and let me hear but. Number three, if the variables are replaced by certain, by some allowable choices, it becomes a statement. Okay. So the set of all these allowable choices, we call it the universe of discourse for that, yes? So the set or a collection of all allowable choices for these variables, for the variables, is called the universe of discourse. Or sometimes for short we just call it the universe. Okay. So still you see that it is a declarative sentence. So the characteristic, the main characteristic is that this declarative sentence contains some variables. It is not a statement, but if the variable or the variables inside that statement, that sentence is replaced by some allowable choices for those variables, then it becomes a statement. Okay, so it seems complicated, but it's much simpler than this. If I want to write the definition is something like this. So let me give you an example for it. Okay. Let the set of integers Z be the universe of discourse. Okay, so then, for example, this declarative sentence that I write is called a predicate or an open statement. For example, I can say x plus 2 is an even number. Okay. Yes. So I have written a declarative sentence. It ends with a full stop. I'm declaring something. So the first condition is satisfied here, but it is not a statement. Why this sentence is not a statement? What was a statement? A statement was a declarative sentence, so that's okay. But it should be either true or false, even if you don't have enough knowledge at the time being, yes? But it should be either true or false. But there is no way to evaluate this sentence, because what we know is that the universe of discourse is Z. It means that, okay, the numbers, the variables are chosen from that set, that's for sure. So I know that this X is an integer because the universe of discourse is Z. But can I make sure that this is true or false, even if I have enough time? No, it depends to my choice, yes? If I choose 1 from the universe of discourse and replace X with 1, then it becomes 1 plus 2 is an even number, then it becomes false. If I choose 2, then 2 plus 2 is an even number, is true, yes? So I cannot just make sure that this is true or false. It doesn't matter how much I spend time on it. So it depends. The truth value of this sentence depends on my choice from the universe of discourse. This is the main difference between a predicate or an open statement with the statement itself. Is that clear? So for example, I can write it as Px. So this is a predicate. So here, for example, I don't need to mention what X is because I have already agreed on that the universe of discourse is Z. But let me see. Let us check again. It contains some variable or variables sometimes. Let me. Okay. It is not a statement, so it contains one variable in our case. It is not a statement for the reason that I told you. But if the variable or variables are replaced by some allowable choices, then it becomes a statement. Yes? So it means that whatever you want to choose from the universe of discourse and replace it instead of X, then you definitely get a statement, either true or false. Is that clear? So that's the meaning of a predicate. Okay, for example, I can have more than one variables. For example, I can assume that Q with X and Y is this sentence, is this declarative sentence. So I can say that, I don't know, for example, 2X and X plus 2Y are even integers. Let me write even numbers. So this is also a declarative sentence. It ends with a full stop, but it contains variables. Here I have only 2 variables, X and Y, and then I have predicate involving two variables, yes? But again, you see that every condition that I was talking about is still fulfilled here. It contains some variables. It is not a statement right now because I cannot evaluate it, no matter how much knowledge I have. It depends to my choices. But when I do that choice, when I actually choose two numbers, one for x, one for y from the set of the discourse, then it becomes a statement, either true or false. Yes? Is that clear? Okay. So that is what I want to mention. Then I want to start this lesson of quantifiers. This is a very important. I have already used them a lot, but let me just study them a little bit systematically here in this lesson. Okay, let me try to evaluate this, make it a little bit simpler, just to motivate you what I mean. So quantifiers are actually a tool in our hand to change predicates into statements. Okay, so for example, let me just write a simpler one. For example, let me just write P of x here with the same universe of discourse. Then I would say that x is an odd number. Okay, so you know that this is a predicate. But if I write it in this way, for every x is an even number, is an odd number. So you see, this was a predicate. This also seems to be a predicate, but do you think this is a predicate, even though it contains variables now? So now this is very important. So I'm using these two words for every x. But where x is coming from, still it's coming from the universe of discourse, okay? So I am talking about that case. For every x is an odd number. Can you just evaluate it right now without knowing the value for x? This sentence can be evaluated true or false. It's a false statement. Do you need to know x? So you see, by writing these two words, these two words and this variable again, I turned this predicate into a statement. So if I want to judge the value of this, I don't need to know the value of x. This is claiming that for every x coming from the set of the coming from the universe of discourse, x is an odd number. You don't need to stay and wait to see what the value of x is. Yes, this is a false statement. Is that understandable for everyone? Is that clear? And then I can write another sentence. There exists an x such that, let me write such that here, such that x is an odd number. I'm just emphasizing again that my universe of discourse is the set of. What do you think? Still, it is a declarative sentence, it contains a variable. But how do you judge this? Do you think this sentence, this declarative sentence, is a predicate now, or is a statement? It's a statement, and because we can just evaluate it. This tells you there exists an x where in the universe of discourse, such that x is an odd number. So is this true or false? Is this true or false? It's true, yes? Without knowing the particular choice of x, you can immediately say that this is true, but that was, for example, false. So it means that even though I have a declarative sentence containing a variable, but then the structure of the sentence changed in a way that this is no longer a predicate, yes? It's a statement. So these things that we write are called quantifiers, okay? Something like this. Oh, sorry. They are called quantifiers. Okay, and then you know that this I always usually use this symbol for every, and then we use, do you remember? This one for there exists, yes? So these are the quantifiers. So now let me introduce them a little bit more formally here. Okay, so let's get rid of this one. Okay.
Mr. Bama,
Yes.
why did you write P x? X is an odd number under the quantifiers.
I will write them. Yes. Yes, you're right. For every x,
I mean,
instead of x is an odd number, I can just write p of x. Is that your question?
Yeah.
I can do that. I just wanted to motivate you what's happening. Okay, so we have in principle 4 quantifiers, but 2 of them are not independent. Okay, so what I mean, let me just start mentioning them. So let's p of x be a predicate.
Mr. Bama,
Yes?
aren't quantifiers just like a special type of input to a function that generates statements?
So if I want to give the role of some kind of a function, I would say that p of x might play the role similar to a function. Because, for example, here, if I ask you, is px true or false, you cannot answer because it depends to my choice. But as soon as I write p2, p2 becomes a statement.
Yeah.
Because then it becomes 2 is an odd number, which is false.
Would 2 be a quantifier?
No, I wouldn't say 2 is a quantifier.
Okay.
Yeah. So I would say, so p of x is a predicate, but when I replace x with a definite value from the universe of discourse, then it turns into a statement. But the problem is that the quantifier here, one way of actually turning, of course, one way of turning by definition itself, one way of turning a predicate to a statement is to replace the variable with some value from the universe of discourse based on its definition. That's the meaning of predicate. But when I use quantifier, I am not replacing the x with any particular number. I am changing a little bit the structure of the sentence that I am saying. Still, you see, the x variable is there, but I'm not claiming that by just writing these 2 words, I am changing the structure of a predicate to a statement.
So quantifiers analyze predicates.
So I would say that a predicate is a tool that somehow, if you put it in the beginning of a predicate, it turns the predicate into a statement without assigning any particular value to the variables, if I want to say something like that. Yes? So let px be a predicate in some universe of discourse, some given universe of discourse. Okay, so we have this. This is called the universal quantifier. Yes, so you have this. You write this, and then you put x, and then you put p of x here. So then you read it in this way. For every x, p of x. So this is called the universal quantifier. Yes? This one is exactly like for all. And this, I think, exists. I will talk about, this is in LaTeX. So the universal quantifier is that one, and then I have the existential quantifier. So this is this. So there exists an x such that p of x. This is how you read this. And these are the fundamental ones. Of course, sometimes, I don't know, do you remember when I was teaching you number theory? No, I can also use this one. So let me clean it. So do you remember, for example, the division algorithm? I think I used this quantifier when I was teaching you this. So assume, do you remember what was the division algorithm? I told you that if you have two integers, a and b is not equal to 0. So do you remember what was the division algorithm? The division algorithm claims that you can find q and r such that this happens, and you also have this, yes? Okay, is less than absolute value of b. That is what we learned there. But then I told you that, so you can write there exists a q where in z. So let me just choose the universe of discourse to be z. So I said there exists a q and there exists an r. But the theorem actually claimed a little bit more. It didn't just claim there exists a q and an r. It claimed, do you remember? There was an adjective I used for that. Unique. Yes? There exists a unique q and a unique r. Yes? And then if I don't know if I have used this before or not, so you put this exclamation mark to emphasize that not only there exists at least one, but that is the only one, not more than that. Okay, so let me write this one. I just want to make sure that you know everything. So I would say the uniqueness quantifier. So this means that I have this, and with an extra exclamation mark, x, px. So if you want to read it, you should say there exists a unique x such that px. This is how you read this. I don't know if this name is universally accepted, but I couldn't find it on the internet. But let me just write something here for you. So non-existential quantifier. So this means that there doesn't exist actually. There is no x px. Yes. So I would write there is no x such that px. Okay, something like this. So these are the quantifiers that at least I know about, but these two are not that ubiquitous in mathematics. And there is a good reason for that. Of course, I use them because sometimes it's easier for me to use these symbols instead of writing those English sentences or any other language sentences. But why do you think people doesn't care about these two that much? There is a mathematical reason behind that. Why we are not that interested logically. So assume that you want to set up a programming language. Might be you don't need to know about these things, okay? But in programming language, there are some ways to implement these ideas in your code, yes? But why we don't need them? Is the question clear? Okay, so why do you think, Alex? Do you want to answer?
It's very hard to tell if something is unique.
No. I mean logically, at the level of logic. For example, this is not, so for example, this example that I refresh your memory about was actually a mathematical theorem, and it's an ancient theorem, by the way. So it's not that hard for our brains to understand the uniqueness, yes? There is another reason that they are not very ubiquitous. The reason is that they can be written a bit, of course, in a little bit more complicated way. These can be written in terms of these, okay? So this is why you don't need them if you want, for example, to develop a language for coding. These can be reduced to this, but of course you need to write more. Okay, now I want to think about this. Can you just write it for me? So for example, this one is easier. Okay, so this tells you there is no x px. I don't need this quantifier if I have already developed all the things that I need, negations and everything. Yes, instead of writing this, I can equivalently write something in front. Yes,
there exists an x such that the negation of p of x.
Getting close, but not exactly. If you think just logically, you understand what's going on. Anyone else? So do you understand my question? My question is that this is read in this way. There is no x such that p of x. There is another equivalent way you can express the same idea, which doesn't use this particular quantifier. Anyone else? Yes, Victor?
For all x, negation.
Yeah, this was correct. So you said there exists, yes. For all x, negation of p of x. Is that understandable? So I am saying that there is no x such that p of x is true, for example. Equivalently, it means that for all choices of x, p of x is not true. That's the equivalent way of saying. So you see that if I already developed the notion of negation, and if I already developed the notion of the universal quantifier, I really don't need to have this quantifier because it is expressible in terms of the previous things. This one is a little bit more complicated. Okay, I want to wait for you. Can you write this one solely in terms of what we have developed so far, including these two that we have learned today? So think about it logically. When you claim that there exists a unique element, what does it mean? No, it's not hard at all. It just because, by the way, logic is something we really follow it in our brain. Yes.
Can we use the sum?
I don't know. This is not my idea, but you can try it. We can just discuss about that. But I mean, don't make it so complicated. Just think. When I say that there is a unique number with that property, what you understand from this sentence? You understand two things. The first thing you understand what? There is a possibility. Yes. So why do you don't dare to talk about that? So this means that there exists, yes, px. This is equivalent, but this is not enough because this might be there are more, but we want to say that there are no more. There is no more actually element. That the other part is hard one to say. So you say this and something. So you see, I am using this quantifier. I am using the conjunction we already learned, but I need to write something else because if I just stop here, it doesn't mean this is equivalent to this. It's not saying the same thing. Agree? Okay. Yes, you want to test your
There exists a y such that py is true and x
so
is not y.
let me. You're saying there exists
a y that isn't x. I mean, if you take it in another order, but
okay.
Such that p of y.
Okay, so there exists a y that y is not equal to x. Okay.
And then p of y.
No, you are actually claiming that there is more. This way, if I understood you correctly, you are saying that there exists a y which is not this x.
There
which
does not
becomes-
exist. There does not exist. I mean.
Okay, but there is not existed. Then you need to translate it in that way somehow, because I am trying to write everything based on the previous what we learned so far. So at least the question is clear, isn't it? I want to write something which means the same thing. And the rule of the game is that you are not allowed to use these two quantifiers. You need to develop something in front of it based on what you have learned so far, and only these two quantifiers you are allowed to use. By the way, this is a good practice. The uniqueness in mathematics means something. What is another way to say that two things are unique? Do you remember? For example, do you assume that you want to show that this is unique? I don't know how much do you remember about what I talked about. So assume that you want to say this is unique. How do you do?
You prove that there are just one answer for Q.
So, but this is hard mathematically. So this is why I'm just trying. So how do you want to say that there is only one answer? Don't ask me. This is the only one. If I insist to ask you, how do you answer me? There is one way. So this is the mathematical logic. I know that you know it, but this is because very natural. You see, I am claiming that there is a unique Q. You don't believe it. If you are believe your friends, we don't have any fight, we go home, okay? But if you want to fight with me, I cannot just say, believe me, there is only one, okay? There is one systematic way that I have to show it to you. Yes?
If we exclude Q, then all possible answers are false.
This is probably one good way, but there's an easier way. I have used this a lot, I think, during the arguments, because they are so natural that I don't need to teach you the logic field to use them. So this is the way. I would say that you don't believe that there is one. Let us say there are two. I show that these two are the same. So this is the best way to show that there is a unique one. If you don't believe that there are two, there are only one, let us assume that there is more than one. Let's say one of them is Q1, the other one is Q2. Okay? Then I show to you that this gives rise to a contradiction. This is one way of doing that. If you assume that there are more than two, there are more than one, I show that accepting this will give rise to a contradiction, which is not possible. Or you can say that, let us assume that Q1 and Q2 are the numbers satisfying this condition. I show that Q1 is equal to Q2. Okay, now, can you just tell me what can I write here now? Everything becomes clear. So let me say Px. If this claim is indeed true, someone says Px is true, someone says Py is true. What you should be able to conclude from this?